Sound Basics Part 1 Introduction. Sound lies at the very center of speech communication. A sound wave is both the end product of the speech production mechanism and the primary source of raw material used by the listener to recover the speaker's message. Because of the central role played by the sound in speech communication, it is important to have a good understanding of how sound is produced, modified, and measured. The purpose of this chapter will be to review some basic principles underlying the physics of sound, with a particular focus on how two ideas that play an especially important role in both speech and hearing: the concept of the spectrum and acoustic filtering. The speech production mechanism is a kind of assembly line that operates by generating some relatively simple sounds consisting of various combinations of buzzes, hisses, and pops, and then filtering those sounds by making a number of fine adjustments to the tongue, lips, jaw, soft palate, and other articulators. We will also see that a crucial step at the receiving end occurs when the ear breaks this complex sound into its individual frequency components in much the same way that a prism breaks white light into components of different optical frequencies. Before getting into these ideas, it is first necessary to cover the basic principles of vibration and sound propagation. A sound wave is an air pressure disturbance that results from vibration. The vibration can come from a tuning fork, a guitar string, the column of air in an organ pipe, the head or rim of a snare drum, steam escaping from a radiator, the reed on a clarinet, the diaphragm of a loudspeaker, the vocal cords, or virtually anything that vibrates in a frequency range that is audible to a listener, roughly 20 to 20,000 cycles per second for humans. The two conditions that are required for the generation of sound wave are a vibratory disturbance and an elastic medium, the most familiar of which is air. We will begin by describing the characteristics of vibrating objects and then see what happens when vibratory motion occurs in an elastic medium such as air. We can begin by examining a simple vibrating object such as the one shown in figure 3.1. If we set this object into vibration by tapping it from the bottom, the bar will begin an upward and downward oscillation until the internal resistance of the bar causes the vibration to cease. The graph to the right of figure 3.1 is a visual representation of the upward and downward motion of the bar. To see how this graph is created, imagine that we use a strobe light to take a series of snapshots of the bar as it vibrates up and down. For each snapshot, we measure the instantaneous displacement of the bar, which is the difference between the position of the bar at the split second that the snapshot is taken and the position of the bar at rest. The rest position of the bar is arbitrarily given a displacement of 0. Positive numbers are used for displacements above the rest position, and negative numbers are used for displacements below the rest position. So, the first snapshot taken just as the bar is struck will show an instantaneous displacement of 0. The next snapshot will show a small positive displacement. The next will show a somewhat larger positive displacement, and so on. The pattern that is traced out has a very specific shape to it. The type of vibratory motion that is produced by a simple vibratory system of this kind is called simple harmonic motion or uniform circular motion, and the pattern that is traced out in the graph is called a sine wave or a sinusoid. We are now in a position to define some of the basic terminology that applies to sinusoidal vibration. Periodic. The vibratory pattern in figure 3.1 and the waveform that is shown in the graph are examples of periodic vibration, which simply means that there is a pattern that repeats itself over time. Cycle. Cycle refers to one repetition of the pattern. The instantaneous displacement waveform in figure 3-1 shows 4 cycles or 4 repetitions of the pattern. Period. Period is the time required to complete one cycle of vibration. For example, if 20 cycles are completed in 1 second, the period is 1/20th of seconds or 0.05 seconds. For speech applications, the most commonly used unit of measurement for period is the millisecond. 1 millisecond is equal to 1/1. 0.000 s is equal to 0.001 s is equal to 10^3 s. A somewhat less commonly used unit is the microsecond. S. 1 microsecond is equal to 1/1 lakh microsecond is equal to 0.00001 microsecond is equal to 10^6 microsecond. Frequency. Frequency is defined as the number of cycles completed in 1 second. The unit of measurement of frequency is hertz, and it is fully synonymous the older and more straightforward term cycles per second, CSPS. Conceptually, frequency is simply the rate of vibration. The most crucial function of the auditory system is to serve as a frequency analyzer, a system that determines how much energy is present at different signal frequencies. Consequently, frequency is the single most important concept in hearing science. Simple vibratory systems of this kind can differ from one another in just 3 dimensions: frequency, amplitude, and phase. Figure 3.2 shows examples of signals that differ in frequency. The term amplitude is a bit different from the other terms that have been discussed thus far, such as force and pressure. As we saw in the last chapter, terms such as force and pressure have quite specific definitions as various combinations of the basic dimensions of mass, time, and distance. Amplitude, on the other hand, will be used in this text as a generic term meaning how much. How much what? The term amplitude can be used to refer to the magnitude of displacement, the magnitude of an air pressure disturbance, the magnitude of a force, the magnitude of power, and so on. In the present context, the term amplitude refers to the magnitude of the displacement pattern. Figure 3.3 shows 2 displacement waveforms that differ in amplitude. Although the concept of amplitude is as straightforward as the 2 waveforms shown in the figure suggest, measuring amplitude is not as simple as it might seem. The reason is that the instantaneous amplitude of the waveform, in this case the displacement of the object at a particular split second in time, is constantly changing. There are many ways to measure amplitude, but a very simple method called peak-to-peak amplitude will serve our purposes well enough. Peak-to-peak amplitude is simply the difference in amplitude between the maximum positive and maximum negative peaks in the signal. For example, the bottom panel in figure 3.3 has peak-to-peak amplitude of 10 cm and the top panel has a peak-to-peak amplitude of 20 cm. Figure 3.4 shows several signals that are identical in frequency and amplitude, but differ from one another in phase. The waveform labeled 0O phase called would be produced if the bar were set into vibration by tapping it from the bottom. The waveform labeled 180O phase would be produced if the bar were set into vibration by tapping it from the top, so that the initial movement of the bar was downward rather than upward. The waveforms labeled 90O phase and 270O phase would be produced if the bar were set into the vibration by pulling the bar to maximum displacement and letting go, beginning at maximum positive displacement for 90O phase and beginning at maximum negative displacement for 270O phase. So, the various vibratory patterns shown in figure 3.4 are identical except with respect to phase. That is, they begin at different points in the vibratory cycle. As can be seen in figure 3.5, the system for representing phase in degrees treats one cycle of the waveform as a circle. That is, one cycle equals 360 O. For example, a waveform that begins at zero displacement and shows its initial movement upward has a phase of 0 degree. A waveform that begins at maximum positive displacement and shows its initial movement downward has a phase of 90 degree, and so on. Figure 3.6. A spring and mass system whose natural vibrating frequency is controlled by two parameters. One, the stiffness of the spring. The stiffer the spring, the higher the natural vibrating frequency. And number two, the mass of the material that is suspended from the spring. The greater the mass, the lower the natural vibrating frequency. We have noted that objects can vibrate at different frequencies, but so far have not discussed the physical characteristics that are responsible for variations in frequencies. There are many factors that affect the natural vibrating frequency of an object, but among the most important are the mass and the stiffness of the object. The effects of mass and stiffness on natural vibrating frequency can be illustrated with the simple spring and mass systems shown in figure 3.6. In the pair of spring and mass systems to the left, the masses are identical, but one spring is stiffer than the other. If these two spring and mass systems are set into vibration, the system with the stiffer spring will vibrate at a higher frequency than the system with the looser spring. This effect is similar to the changes in frequency that occur when a guitarist turns the tuning key clockwise or counterclockwise to tune a guitar string by altering its stiffness. The spring and mass systems to the right have identical springs but have different masses. When these systems are set into vibration, the system with the greater mass will show a lower natural vibrating frequency. The reason is that the larger mass shows greater inertia and consequently shows greater opposition to changes in direction. Anyone who has tried to push a car out of a mud or snow by rocking it back and forth knows that this is much easier with a light car than a heavy car. The reason is that more massive car shows great opposition to changes in the direction. In summary, the natural vibrating frequency of a spring and mass system is controlled by mass and stiffness. Frequency is directly proportional to stiffness, SF, and inversely proportional to mass, MF. It is important to recognize that these rules apply to all objects and not just simple spring and mass systems. For example, we will see that frequency of vibration of the vocal folds is controlled to a very large extent by muscular forces that act to alter the mass and stiffness of the folds. We will also see that the frequency analysis that is carried out by the inner ear depends to a larger extent on a tuned membrane whose stiffness varies systematically from one end to the cochlea to the other. Sound propagation. As was mentioned at the beginning of this chapter, the generation of sound wave requires not only vibration but also an elastic medium in which the disturbance created by the vibration can be transmitted. Bell jar experiment described in Patrick Science book, not yet written, to say that air is an elastic medium means that air, like all other matter, tends to return to its original shape after it is deformed through the application of a force. The prototypical example of an object that exhibits this kind of restoring force is a spring. To understand the mechanism underlying sound propagation, it is useful to think of air as consisting of collection of particles that are connected to one another by springs, with the springs representing the restoring forces associated with the elasticity of the medium. Air pressure is related to particle density. When a volume of air is undisturbed, the individual particles of air disturb themselves more or less evenly, and the elastic forces are at the resetting state. A volume of air that is in this undisturbed state, it is said to be atmospheric pressure. For our purposes, atmospheric pressure can be defined in two terms: interrelated conditions. One, the air molecules are approximately evenly placed. Two, the elastic forces represented by the interconnecting springs are neither compressed nor stretched beyond their resting state. When vibratory disturbances cause the air particles to crowd together, that is, producing an increase in particle density, air pressure is higher than atmospheric and the elastic forces are in a compressed state. Conversely, when particle spacing is relatively large, air pressure is lower than atmospheric. Figure 3.7 shown above is highly schematic illustration of the chain reaction that results in the propagation of a sound wave, modeled after Dennis and Pinson 1963. When a vibrating object is placed in an elastic medium, an air pressure disturbance is created through a chain reaction similar to that illustrated in 3.7. As the vibrating object, a tuning fork in this case, moves to the right, particle A, which is immediately adjacent to the tuning fork, is displaced to the right. The elastic force generated between particles A and B, not shown in the figure, has the effect of split second later of displacing particle B to the right. This disturbance will eventually reach particles C, D, E and so on. And in each case, the particles will be momentarily crowded together. This crowding effect is called compression or condensation, and it is characterized by dense particle spacing and consequently air pressure that is slightly higher than atmospheric pressure. The propagation of the disturbance is analogous to the chain reaction that occurs when an arrangement of dominoes is toppled over. Figure 3.7 also shows that at some close distance to the left of a point of compression, particle spacing will be greater than average and the elastic forces will be in a stretched state. This effect is called rarefaction and it is characterized by relatively wide particle spacing and consequently air pressure that is slightly lower than atmospheric pressure. The compression wave along with the rarefaction wave that immediately follows it will be propagated outward at the speed of sound. The speed of sound varies depending on the average elasticity and density of the medium in which the sound is propagated, but a good working figure for air is about 35,000 centimeters per second or approximately 783 miles per hour. Although figure 3.7 gives a reasonably good idea of how sound propagation works, it is misleading in two respects. First, the scale is inaccurate to an absurd degree. A single cubic inch of air contains approximately 400 billion molecules and not the handful of particles shown in the figure. Consequently, the compression and the rarefaction effects are statistical rather than strictly deterministic as shown in figure 2nd, although figure 3.7 makes it appear that the air pressure disturbance is propagated in a simple straight line from the vibrating object, it actually travels in all directions from the source. This idea is captured somewhat better in figure 3.8, which shows sound propagation in two of the three dimensions in which the disturbance will be transmitted. The figure shows rod and piston connected to a wheel spinning at a constant speed. Connected to the piston is a balloon that expands and contracts as the piston moves in and out of the cylinder. As the balloon expands, the air particles are compressed, that is, the air pressure is momentarily higher than atmospheric. Conversely, when the balloon contracts, the air particles are sucked inward, resulting in rarefaction. The alternating compression and rarefaction waves are propagated outward in all directions from the source. Only two of the three dimensions are shown here. That is, the shape of the pressure disturbance is actually spherical rather than the circular pattern that is shown here. Superimposed on the figure in the graph labeled one line of propagation is the resulting air pressure waveform. Note that the pressure waveform takes on a high value during instants of compression and a low value during instants of rarefaction. The figure also gives some idea of where the term uniform circular motion comes from. If one were to make a graph plotting the height of the connecting rod on the rotating wheel as a function of time, it would trace out a perfect sinusoid, that is, with exactly the shape of the pressure waveform that is superimposed on the figure. We now arrive at what is probably the single most important concept for understanding both hearing and speech acoustics. The graphs that we have used up to this point are for representing either vibratory motion or the air pressure disturbance created by motion are called time domain representations. These graphs show how instantaneous displacement or instantaneous air pressure varies over time. Another method for representing either sound or vibration is called frequency domain representation, also known as spectrum. There are, in fact, two kinds of frequency domain representations that are used to characterize sound. One is called an amplitude spectrum, also known as magnitude spectrum or a power spectrum, depending on how the level of the signal is represented. And the other is called phase spectrum. For reasons that will become clear soon, the amplitude spectrum is by far the more important of the two. An amplitude spectrum is simply a graph showing what frequencies are present with what amplitudes. Frequency is given along the x-axis and some measure of amplitude is given on the y-axis. A phase spectrum is a graph showing what frequencies are present with what phases. Figure 3.10 shows examples of the amplitude and phase spectra for several sinusoidal signals. The top panel shows a time domain representations of a sinusoid with a period of 10 millisecond and consequently a frequency of 100 Hz. The peak-to-peak amplitude for this signal is 400 PA and the signal has a phase of 900 degrees. Since the amplitude spectrum is a graph showing what frequencies are present with what amplitudes, the amplitude spectrum for this signal will show a single line at 100 Hz with a height of 400 PA. The phase spectrum is a graph showing what frequencies are present with what phases. So, the phase spectrum for this signal will show a single line at 100 Hz with a height of 90 degree. The second panel in figure 3.10 shows a 200 Hz sinusoid with a peak-to-peak amplitude of 200 PA and the phase of 180 degree. Consequently, the amplitude spectrum will show a single line at 200 Hz with a height of 100 PA, while the phase of spectrum will show a line at 200 Hz with a height of 180 degree. To summarize, 1. A complex periodic signal is any periodic signal that is not sinusoidal. 2. Complex periodic signals have energy at the fundamental frequency and at whole number multiples of the fundamental frequency 2, 3, 4 and 3, although measuring the fundamental frequency allows us to determine the frequency locations of harmonics, there is no simple measurement that can tell us harmonic amplitudes or phases. For this, Fourier analysis or some other spectrum analysis technique is needed. We will also see that a crucial step at the receiving end occurs when the ear breaks this complex sound into its individual frequency components in much the same way that a prism breaks white light into components of different optical frequencies.